In this section, we show that despite the complex electronic structure of semiconductors, there are so few electrons or holes that we need to take account of. We can use classical statistics and classical transport equations for semiconductors. Recall that in a typical semiconductor like silicon, each atom has 4 bonds that make up the valence band of the semiconductor. We can schematically draw these 4 bonds in 2 dimensions, although silicon's bonds are tetrahedrally coordinated, making it a 3-dimensional covalent solid. In the textbook, each of these entirely filled valence band bonds are drawn as double lines where each line represents 1 electron. In a semiconductor, an electron and hole pair can be created by a photon or thermal excitation of an electron across the band gap. At a local level, we can think of this as the photon breaking the bond, moving the electron out of the bonding network into the conduction band where it behaves like a free electron. For thermal excitation, we can think of the motion of the atoms as stretching the bonds, which will sometimes break a bond. This removes the electron from the bonding network and allows it to transport freely in the conduction band. In both of these cases, the broken bond leaves a hole in the bonding network that will have a net positive charge. This gives us both a hole and an electron for each excitation. An electron from a neighboring bond can move to a localized hole, which has the effect of the hole moving in the opposite direction that the electron moved. In our block band diagrams, because electrons prefer to be lower in energy, the holes will appear at the top of the band. We can also think of holes at the top of the valence band as having virtually no energy penalty to move from right moving states to left moving states, therefore allowing electrical conduction. But because a hole in the right moving states is actually an extra electron in the left moving states, the effect of a hole in the right moving states is that of a positive charge moving to the right. When an electric field is applied to a material in the x direction, that means the electric potential changes linearly from one x position to another. The applied electric potential leads to a change in the electrostatic potential energy of electrons in the material. For such a problem, we typically draw our energy block diagram as a function of position using the horizontal axis for position. Because the electrostatic potential energy of an electron changes with position, the wave function energy of the valence band and conduction band states will change accordingly. This appears as a distortion in our block band diagrams that we call band bending. Because in semiconductors we have both electrons and holes, we need to consider their contributions to electrical conductivity separately. We think of electrons in the conduction band and holes in the valence band as having different mobilities and different drift velocities, keeping in mind that because the holes are positively charged, they will drift in the opposite direction as electrons. We think of electrons and holes as transporting charge independently and parallel with one another, so that the total conductivity of a semiconductor can be thought of as the sum of the contribution of the conductivity of electrons and that of holes. We often reserve N for the electron concentration of the conduction band and then use P for the hole concentration in the valence band. For an intrinsic semiconductor, where we have similar number of electrons in the conduction band as holes in the valence band, the Fermi level will be within the band gap between the conduction band bottom and the valence band top. For electrons close to the band edge, we can approximate the density of states with our 3D electronic density of states, which is proportional to the energy from the bottom of the band to the 1/2 power. For the holes at the top of the valence band, we will have a very similar density of states, again proportional to the square root of the energy difference to the valence band edge. Because the Fermi level is so far from the conduction band edge, the Fermi function for electrons will be very close to that of the Boltzmann distribution. The exponential dependence of the Boltzmann distribution tells us that most of the electrons in the conduction band are actually very close to the conduction band edge. Because the probability of finding a hole is simply 1 minus the probability of finding an electron, we can use 1 minus the Fermi function for the probability distribution function for holes. Again, for a Fermi level in the band gap sufficiently far from the valence band edge, the exponential dependence of the Boltzmann distribution suffices, telling us that most of the holes are very close to the valence band edge. We can apply these approximations quantitatively to derive the density of electrons or holes in a semiconductor. When the Fermi level is within the band gap further than kT from the conduction band edge, we can approximate the Fermi distribution function with the Boltzmann distribution function. This tells us that most of the electrons are actually near the conduction band edge, and so we can use the density of states near the conduction band edge approximated as the free electron density of states of a parabolic band, giving us the density of states as a function of energy is proportional to the energy difference from the conduction band edge to the 1/2 power. Notice that here we have used the effective mass, not the actual mass of an electron, because the effective mass tells us the effective curvature of the band near the band edge. For a rough approximation of the number of electrons, shown here in red, we will approximate this with a rectangle. The height of the rectangle given by the energy range that most of the electrons are in, or delta E. The width of the rectangle approximated by the average density of states of those electrons and their occupation probability F. We approximate that this average energy above the conduction band edge is proportional to the thermal energy, or kT. Then, ignoring the numerical constants, we have effective mass to the 3/2 times kBt to the 1/2 power from the density of states equation. Then we have the kT from our delta E. And then from the Boltzmann distribution function, we have exponential of the difference between the Fermi level and the conduction band edge over kT. This gives us the density of electrons in the conduction band is exponentially proportional to the difference between the Fermi level and the conduction band edge divided by kT times a numerical constant we call the effective density of states, where the effective density of states depends on the effective mass of the conduction electrons and kT. This effective density of states has units of number of states per volume because it is the density of states, which normally has units of states per volume per energy, times an energy, or kT. The exact equation from the previous slide can be derived analytically using a useful method of mathematical physics. The goal here is to solve for the number density of electrons using our approximation for the density of states and the Boltzmann distribution function. The strategy is to turn this integral into a dimensionless integral with definite limits. In this way, the integral will become just a numerical factor that is typically between 1 and 10. In this case, our definite integral is shown here. The dependencies on physical quantities such as mass and temperature will be known even if we can't do the integral. We will also get factors of h and kb correctly because of the dimensional analysis of the problem. Here we use the dimensionless quantity x, which is the energy above the conduction band minimum, divided by kT. X is dimensionless because both of these terms have units of energy. We will use x for our integration to get n, so we need a change of variables from e to x. Moving kT over to the other side, we can take the derivative of both sides to get dE in terms of dx. Our first step is to write our distribution function of energy into units of energy relative to the conduction band minimum that we need for our new variable x. We can do that by adding and then subtracting EC in the numerator of our exponential. This gives us two exponentials, one E minus EC and then the other EC minus EF. We then get what we recognize as our new variable x, and then a quantity that doesn't depend at all on the integration variable e. This gives us e to the minus x and an exponential that depends on the difference the Fermi energy is from the conduction band minimum. Our density of states equation, which has E minus EC, or E relative to the conduction band minimum, to the 1/2 power, can be changed to x by dividing and multiplying by kBt to the 1/2 power. This gives us a kBt on top to the 1/2 power and our integration variable x to the 1/2 power. Combining now our equation for n that contains g of e, f of e, and dE gives us the expression here, which has kt to the 3/2 power, 1/2 coming from our density of states change of variables, and the kt to the 1 power coming from our change of variables for dE to dx. The effective mass to the 3/2 power comes directly from the density of states, and then our exponential of the Fermi level relative to the conduction band minimum comes from our Fermi function. The integration is now x to the 1/2 e to the minus x from 0 to infinity, because the energy went from 0 to infinity, and so does x. This definite integral is a dimensionless quantity that we can look up, and it turns out to be 1/2 of the square root of pi. Putting all of these constants together gives us the equation we had before, which we summarize in the next slide. In summary, the density of free electrons in the conduction band of a semiconductor depends exponentially on the difference between the Fermi level and the conduction band minimum relative to kT. It also depends on a numerical value we call the effective density of states, which has units of number per volume, like n, the electron concentration. The effective density of states depends on the effective mass, like the true density of states, but also it depends on temperature, because at higher temperatures, more states are effectively available to the electrons. Following the same procedure for hole concentration results in similar expressions. For hole concentration, we measure the Fermi level relative to the valence band edge instead of the conduction band edge. Also, the sign is reversed for the energy, reflecting the fact that higher energy holes are low in the valence band, whereas at the top of the valence band, the holes have the lowest energy. The effective density of states in the valence band is similar to that of the conduction band, except we use the effective mass for holes instead of that for electrons. Notice that if we multiply n times p together, we will have an exponent with minus EF and another with an exponent of minus positive EF, such that the EF terms will cancel. Thus, the product of n times p together will depend only on the difference between the conduction band energy and the valence band energy, which is also the band gap. Here we see the NP product has this exponential of the band gap over kT times the effective density of states of the conduction band times the effective density of states of the valence band. We think of this value as a constant because it doesn't depend on the Fermi level anymore, which depends on doping. It only depends on the material's properties, effective mass of the conduction band, effective mass of the valence band, the band gap, and temperature. We call this product the square of the intrinsic concentration because when n is approximately equal to p, both n and p are equal to the intrinsic concentration. Even when n is different from p, for example by doping, the product n times p is always a constant. Thus, if n is increased, then p must decrease, keeping the product constant. We call this the mass action law, an analogy to the thermodynamics of a chemical reaction. We can think of our equilibrium chemical reaction of an electron plus a hole annihilate each other into nothing plus energy. We think of the reverse reaction as the generation of an electron and hole pair from the addition only of energy. The forward reaction also describes the recombination of an electron and a hole to produce energy. From chemical thermodynamics, we know that when electrons and holes are in thermodynamic equilibrium, the product of their concentrations should be a constant, and that the constant should depend exponentially on the energy of the reaction relative to kT. For our recombination of electron and holes, this energy difference is the band gap. We can then use these expressions for n and p to solve for the exact location of the Fermi level within the band gap, and show that it depends on temperature, the effective mass of the conduction and valence bands, and the doping. We start by considering the ratio of n divided by p, which gives us the ratio of the effective density of states of the conduction band divided by that of the valence band. Then, in the exponent, we get the argument of the exponent for the n minus the argument for the exponent for p. Taking the logarithm of both sides will allow us to solve for the Fermi level. This gives us the logarithm of the concentration ratio n over p and the logarithm of the effective density of states ratio, which we move to the other side. Then from the exponential, we see we have minus EF, which is plus EF, plus another EF, minus EC, minus EV, giving us 2EF minus EC minus EV, and then we move the KBT over to the other side. Solving for EF now, we see that we have EC plus EV over 2, which is the average of the conduction band energy plus the valence band energy, or the midpoint of the band gap. Then we also have two terms that depend on temperature, which tell us right away that at temperature 0 Kelvin, the Fermi level is exactly at the midpoint of the band gap. Because we are more familiar with band masses rather than the effective density of states, we can replace the logarithm of the ratio of the effective density of states with the logarithm of the ratio of the effective masses. Because the power of the effective mass is to the 3/2 power, we multiply by another 3/2, getting 3/4 here. From the two temperature dependencies given here, we see that even for intrinsic semiconductors, where n is approximately p and the logarithm is essentially 0, we still have a temperature dependence of the Fermi level, with the Fermi level moving towards the band of lighter mass. This is because if the Fermi level didn't move, then the band with heavier mass would have more carriers, no longer keeping n equal to p. We have found in this section that we can use the classical description for the charge carriers in semiconductors despite the complex band structures that come from quantum mechanics. Although the quantum mechanical electronic states are not free electron bands, as long as we restrict ourselves to considering only electrons in the conduction band and the holes in the valence band, the dispersion relation around these charge carriers is nearly parabolic that can be described with an effective mass. Even the valence band can be described with a positive effective mass as long as we think of the charge carriers as positively charged holes where their lowest energy is at the top of the band. When the Fermi level is within the band gap, there are so few electrons just at the bottom of the conduction band and so few holes just at the top of the valence band that classical Boltzmann statistics works quite well. This is because there are many more possible electronic states than available electrons or holes, so that the Pauli exclusion principle has little effect. Even the kinetic energy, or average energy, of the electrons above the conduction band edge is like that of a classical gas 3/2 kBt. Because all of these electrons are free to participate in electrical conduction like a free electron gas, we can use this energy to calculate the thermal velocity of electrons, which comes out to be 10 times lower than the Fermi velocity in metals.